Okay, so I'm going to start with just doing the statically indeterminate systems part of number 5, and then I'll do number 6. Um, so we have this column made of steel, given cross section, given length. Um, so at its initial temperature and before the 20,000 Newton force is applied, the reactions are 0. Okay, so that's kind of, we usually take that as sort of given. Um, that's just saying if you didn't have that force and at the starting temperature, there's no like preloading of this thing. Um, what are the reaction forces if all these problems have these crazy changes in temperature? If you ever have a column this big that decreases 230 degrees Celsius, like you have a lot bigger problems than okay, so, and that force, does it say it at the midpoint? Yeah. So we're going to start by doing the statics. And then what we're going to see is that it's a statically indeterminate system. You always see that once you get your equations from the statics. And then we'll proceed from there. So free body diagram. I'm going to say that there's a reaction force this way and this way. And at the midpoint, there's a force up of 20,000 newtons. And so I'm just choosing, I'm not trying to guess about the directions of these forces. I'm just choosing kind of like in the positive y direction. And then, the signs will work out on their own. So Newton's second law, just in the vertical direction, because nothing else is happening in any other directions, says RA plus RB plus 20,000, all these things are acting in the same direction, is equal to 0. So RA plus RB is equal to negative 20,000. And this is the point where if you weren't doing these problems from a set of problems that says statically indeterminate systems, this is where you would see this is statically indeterminate. Okay, you've done the statics. There's nothing else that statics can help you with, and you have two variables for one equation. We could do statics in other directions and a moment equation, but you would just get 0 equals 0 for all that other stuff. This is the only useful equation, and it's not enough to solve. Okay. Okay, so this is statically indeterminate. So now you can take 5 seconds or some small reasonable amount of time and feel sorry for yourself and then go on. And so now we're going to calculate the change in length. And eventually we're going to say that that change in length has to be 0 because this thing is locked between a fixed floor and ceiling. And there are two things that are going to contribute to changing the length. One is the elongation and compression due to internal tension. And then the other one is thermal expansion from the temperature change. Anybody have a guess, by the way? Like, look at this problem and tell me, what do you think's going to happen here?
One on the bottom is going to be rounded, and the one on the top is going to push as like how I envision it.
I think really you're going to have pretty similar magnitudes of forces at the top and the bottom here. And they're both going to be away from the bar. So the bottom force is going to be downwards and the top force is going to be upwards. Anybody have a explanation for why I'm saying that? Well, because of this huge change in temperature, that 20,000 Newton force is going to get kind of dwarfed by the effect of the thermal stuff. And what's happening is this temperature change is going to make this bar want to shrink. It's going to try to contract. And since it can't contract, it's attached to the floor and the ceiling. The floor and the ceiling are going to have to pull really hard to re-stretch it back to its original length. Okay. So that 20,000 is actually going to be sort of a minor character in this just because of that huge change in temperature. Um, if this was a more reasonable temperature, like 5 degrees Celsius, then maybe it's a little harder to figure out what's going on. But it's all happening at once, but you can think of it as kind of in steps. The temperature shrinks it, and then the floor and the ceiling say, oh, no, you don't. Like, come back here, stretch it back. So, okay, so I'm going to start by calculating the internal tension at the different spots. So we can calculate the elongation or compression due to internal tension. So I'm going to do my cuts. My first one, this has a length of 1 meter. So the first one goes to the midpoint. And like I usually do, I'm going to imagine tipping this beam over to the right. So when I do my cut, we have our RA this way. We haven't made it to the 20,000. And then the internal load is this. And you could do your V and M and fancy T and everything, but they just come out being 0. The only stuff that's non-zero is along the beam's axis. And so Newton's second law says RA plus T is equal to 0. So T is equal to negative RA. And then we'll go to cut 2. We still have RA. This time we've made it past the 20,000, which would be going this way. And then here's our internal tension. So Newton's second law in this direction says RA plus 20,000 plus T is equal to 0. So the internal tension for this part is negative RA minus 20,000. And now that we have those, we can do our elongation calculations due to this internal tension. So the elongation is TL over EA. So for the first half, our T is negative RA. Our L is 0.5. Our E, this is steel, so we have 200 times 10 to the ninth. And then our cross-sectional area is 0.03 square meters. And then we have to add that, so that's the elongation of like the bottom half of this beam. And now we need to add that to the elongation of the top half of this beam, which is the quantity negative RA minus 20,000 times the length of the top half is also 0.5. And then we have 200 times 10 to the 9 times 0.03. And if I multiply this all out, I can just simplify this. So I have, I'll do the other one too here. Okay, so I have 1.6 repeating times 10 to the minus 10 times RA, and that's negative. And then minus
Would the bottom just cancel out?
it. In this case, it's not going to. So our total. So we're going to put. I mean, that's a really good question, and it often does, but it only cancels out in certain cases where the only thing going on is internal tension. In this case, we also have a change in length due to thermal stuff, and that's the reason it won't cancel out. Okay, minus 1.6 repeating times 10 to the minus 6. That's our simplified form of the elongation due to internal tension. And now we'll go to the thermal calculation. And I have to look up the coefficient of thermal expansion for steel. It's somewhere, I think, around 1 times 10 to the minus 5, but let's just look it up. So let's call it 1.2 times 10 to the minus 5. So our alpha is, we're going to call it 1.2 times 10 to the minus 5, 1 over degrees Celsius. And there's no tricky stuff we have to do here. We can just treat it all as a single length. We don't have to break it up or anything. So the thermal change in length is 1.2 times 10 to the minus 5 times the full length of 1 times the change in temperature, and this decreases 230 degrees Celsius, so minus 230. One 1.2 times 10 to the minus 5. And so if this bar was free to do what it wanted and you decrease the temperature this much, you would get a change in length of negative 0.00276. So this 1 meter bar would decrease 2.76 millimeters. Okay. Well, so basically, in order to keep the length the same, we're going to have to stretch this bar now 2.76 millimeters. And think of how much force you have to apply to a steel bar with a relatively big cross section in this case to make it stretch, 2.76 millimeters. It's a lot of force. That's why these reactions are going to be big. So the total elongation is negative 1.6 times 10 to the minus 10 RA minus 1.6 repeating times 10 to the minus 6 minus 0.00276. And this has to be equal to 0. That's our restriction on that comes from the setup of this problem. And so 1.6. And what you get is that RA is equal to negative 1.657 times 10 to the 7th. And this is in newtons. Now we can plug that into our statics equation. It says, so negative 1.657 times 10 to the 7 plus RB has to be equal to 20,000. Or was it negative? Negative 20,000. But that 20,000 you can see isn't going to matter much compared to this is 2 times 10 to the 4th. This is 1.66 times 10 to the 7th. The 20,000 barely even comes into this, depending on how much you round. And so RB is equal to 1.655 times 10 to the 7th. That RA force is acting down at the ground, and at the ceiling, that RB is acting up. And that's consistent with having to apply forces that stretch the hell out of this thing to make it stay in its spot. Okay. And that's all you wanted to see, right, Owen? That part?
Yeah.
Okay.
I know.
Any other questions about that one? Okay, and next is number 6.
When it says sprint filter on some point away for the
Yeah.
it's basically just choose any point of it.
Yeah, so the way to go then, let's see. So what's the stress tensor? Oh, okay. So well, that's actually a little funny, because the stress tensors are going to change above and below that 20,000 Newton force, although they're not going to change very much. Maybe I was just using the fact that the effect of the 20,000 is pretty minimal in this problem. But yeah, you can pick any point you want there. So why did I say away from the ends at all? Why not at the end?
Because points at the end are less reliable.
They're less reliable. Yes. Saint Venant's principle says that we can trust our answers as you get away from the ends a little bit. You don't have to get very far away, but at the ends there's going to be stress concentrations that we don't have the ability to calculate. Anyone know what numerical approach you would use to calculate the stresses, like in those complicated areas at the end? Starts with an F. Yes, exactly. That's right. You would use finite element analysis to do that. The best mathematical mechanics people in the world, mechanics is kind of a mathematical thing, and there are still people who do mechanics problems by hand and publish papers on it and stuff. But for them, there's still quite a limit to how complicated problems can be, and that they can still calculate closed form solutions using differential equations. But there's like no limit for finite element analysis. You can make your meshes closer, put your points closer and closer together, get better and better approximations. And that's how you would do it if this was a thing inside an engine and you needed to know what was going on. You would use finite element analysis. Any other questions about that one? Did I already do this? Okay, so this one is torsion, not tension and compression. And it gives us a cross-sectional area. For each of those two halves. And we want to calculate the reactions at the walls. And the reactions we're talking about here are torques. They're couples at the wall that are parallel to the horizontal axis. All right, so we're going to start out with a free body diagram. Like we go into this always optimistic, like maybe statics will do this for us. But if there should probably be a limit to your optimism about that when you're doing problems under a heading that say statically indeterminate systems, Okay, so let's call this torque A, fancy TA. And then over here, we'll call this TB. And then at the middle of the left half, we have 4,000 this way. This is also a torque. And then at the middle of this one, we have a torque going the other way of 1,500. And rotational Newton's second law, looking only at x components of moments, we have fancy TA plus 4,000 minus 1,500 plus TB is equal to 0. And so fancy TA plus fancy TB is equal to negative 2,500. And that's all the statics we have. And it's one equation with two variables, so we can't do anything about that. And so now we're going to go to the cuts. We're going to calculate the internal torques. And then we're going to use those to calculate the angle of twist. And the total angle of twist, because this thing is fixed between two walls, those two connections to the wall keep it from, it doesn't allow one end to rotate. There can be rotations of points in between the two endpoints, but at the two endpoints, it has to be where it started because it's welded there. Okay. Same thing with by the way, with this, saying that the total elongation of this doesn't change. That's not saying that the midpoint isn't moving somewhere. It is. And every point away from the ends is moving somewhere. But the full length ends up being exactly 1 meter. Okay. All right, so we're done with the statics. So now we're going to go to the cuts. And there are only, we need 3 cuts. We need a cut that represents the stuff before the 4,000, a cut that represents all the stuff between the 4,000 and the 1,500, and then a cut that represents all the stuff after the 1,500. So this is 0.3 meters. So the midpoint is 0.15. So the 4,000 is at 0.0715, at 0.075. So our first cut is going to be valid for 0 to 0.075. And all we have is the torque, fancy TA, and then an internal torque, fancy T. And the moment equation about the x-axis says fancy TA plus fancy T is equal to 0. And so the internal torque for this piece is negative fancy TA. And then we'll do our second cut that's valid from 0.075 to 0.075 plus 0.15. So that is 0.225. So this is the range of possible x values for this. And this time it's going to go, so we're dealing with something past that first torque of 4,000. We have our fancy TA here, and then we have our fancy T. And all we know is that the right end goes past the 4,000, so it's possible we haven't gotten to that smaller cross-sectional area yet. But the cross-sectional areas do not affect the internal loads, so you don't have to worry about that when you decide what your cuts are. All that matters are those external torques. The moment equation, we have TA plus 4,000. This shouldn't be TA, this should just be T. Plus T is equal to 0. And so the internal torque on this piece is negative TA minus 4,000. And then cut 3 is valid from 0.225 to 0.3. And this time we're talking about a right end that's past the 1,500 Newton meter torque. So we've gotten to here, and then we've gotten to somewhere like this, and there's a 1,500 Newton meter torque like this. There's a 4,000 like this. There's a fancy TA like this. And then there's an internal torque. So fancy TA plus 4,000 minus 1,500 plus fancy T is equal to 0. So fancy T is equal to negative TA minus 2,500. And now that we have expressions for all of the internal torques, now we can use our calculation for the angle of twist. So remember that our angle of twist is the sum over all the pieces that we need. In this case, it's 3 pieces of the internal torque of the piece times the length of the piece divided by the material stiffness in torque, that is G, times the geometric resistance to twisting, which is the polar moment of inertia in the case of twisting. And now we can fit these pieces together. G is equal to, so let's see what this is. What are the reactions of the walls? So this is a case where there's no thermal anything, no thermal effects. And every piece has the same value of G. And so that G is going to cancel out of everything. The I sub P is going to be different for the different parts. So let's see. So that G is irrelevant, and that's why it isn't given. This answer would be the same if this was hard rubber as it would if it was steel, as if it was anything. These answers would be the same. That's what it means that G is canceling out. Okay, so the polar moment of inertia for the left is pi over 2 times the radius to the 4th. So that is, on the left part, that is 0.02. No, okay. I entered that wrong. It told me something to the times 10 to the minus 27th. Okay, so on the left part, the polar moment of inertia is 2.5133 times 10 to the minus 7 meters to the 4th. And then on the right half, that radius is 0.01. By what factor is this going to decrease? I could get this answer by just multiplying. What?
16, right?
It is going to decrease by, so the factor is going to be 1 over 2 to the 4th, which is 16. Yeah, very good. Okay, so the polar moment of inertia for the right part is pi over 2 times 0.01 to the 4th. And so that is 1.5708 times 10 to the minus 8. And so now our angle of twist, we have to think a little bit about these pieces. So our first piece is going to have a length of 0.075. It's going to go from the left end to the 4,000. Our second piece is going to go from the 4,000 to where the area decreases. Our third piece is going to go from where the area decreases to the 1500. And our fourth piece is going to go from the 1500 to the right end. Anybody have any questions about why that is? You follow me on that? Because if you look at this formula, you need a new piece anytime any of these things change. So if that internal torque changes, you need a new piece. If the I sub P changes, you need a new piece. Okay, so the angle of twist is, the first piece is negative TA times 0.075 divided by a G that we won't care about times 2.5133 times 10 to the minus 7. Then the second piece just goes from the 4,000 to the end of the fatter part. So this has an internal torque of negative TA minus 4,000. And the length of this piece is also 0.075. And then we're dividing by G times the polar moment of inertia from the fatter section. And then we go to the third piece. That still has the same internal torque. So negative TA minus 4,000. And the length of this piece is 0.075 divided by G. But then this time we have the polar moment of inertia for the thinner piece. So this is 1.5708 times 10 to the minus 8. And then finally, the fourth and last piece, the internal torque is, this should be TA, not T. The internal torque is negative TA minus 2,500. The length of this piece is 0.075 divided by G times the polar moment of inertia for the thinner piece, 1.5708 times 10 to the minus 8. And all this is equal to 0. And since everything's divided by G, you can multiply both sides by G and get rid of that. That's why that doesn't come into the calculation. And so, yeah, you can. That's right. Okay, so minus 4.2972 times 10 to the 11th is equal to 0. And so TA is equal to negative 3272.8 Newton meters. Then you can plug that back into our statics equation to find TB. Here was our statics equation. So they have to add up to be negative 2,500. And so negative 3272.8 plus TB is equal to negative 2,500 So TB is equal to positive 772.8 Newton meters. So we had so we have the 4,000 going this way, the 1,500 going this way. TA is going this way with a magnitude of 3272.8, and TB is going this way with a magnitude of 772.8. Any questions about that? So we got some weird effects here, I guess, because of the changes in geometry. You would think both of these two torques would be opposite the 4,000, but that's not how it worked out. It gets a little more complicated than that because of the change in geometry. Okay. So now we're talking about, so back to beam displacements and statically indeterminate systems. We've done elongation and contraction due to internal tension and thermal expansion. Okay. And we've done angle of twist, and we've done statically indeterminate systems related to both of those. The last thing that we have left is deflection due to bending moment. I mentioned this last time, but I'll mention it again. I mean, you might think like, wait, we skipped shear force. Why we jumped straight to bending moment and then that's the last one? What about changes in shape due to shear force? Well, you're going to see that this is a differential equations approach that we use, and because of the differential the derivative relationship between shear force and bending moment, these two are combined into one thing. So it's not like shear force isn't there, but we just don't need it. Bending moment gives us everything we need. Okay, so this is going to depend on the theory of elastic beams. um, and these are also known, by the way, as Euler-Bernoulli beams. Those are two good math guy names. If you ever don't know the name of an engineering thing, Euler is a good guess. And the theory of elastic beams says if you take the bending moment at a single point and divide it by E times I, so E is the Young's modulus, I is the area moment of inertia, and these two things together have a name. Together, their E times I is called the flexural rigidity. Because they determine how easy or hard it is for a beam to be bent. M over EI is equal to the curvature of the beam which is usually denoted with the Greek letter kappa, just for future reference or whatever. Okay, what do we need from these beams? We need them to be, so in order to roughly satisfy this, we need them to be slender and long. And I guess let's put elastic in here too. The curvature of a function. So now we have to think about what this curvature means. What's curvature? The curvature of a function f, and let's think of a function f of x, is given by this pretty ugly looking formula. It's the second derivative in absolute value divided by, so in the denominator we have the quantity 1 plus the square of f prime of x, and then all of this stuff is to the power of 3/2. Okay, well, we'd rather not deal with that. That's ugly. But we're going to be rescued here again by the fact that we're assuming small deformations. Okay. So what happens if you have very small deformations? So if they're small enough, notice that the effect of that is, so let's think of a function representing the height of the beam at every point. Okay, so let's say that this is the beam's original position. And let's say that we have really small deformations, and so this beam is just going to do stuff like this. Okay, so red is the undeformed height of the beam. And green is the deformed height after you apply the loads. Well, notice that we had these very small deformations, and they were so small that the slope of this green line also stayed close to 0. Like, think of what it would take for the for the slope of the green line at any point to deviate far from zero. You'd, if you integrated that over any distance, for it not to, so you would need that displacement to change. I guess you wouldn't really mathematically need that. Most likely that's what it would be. You could have a case where this thing was doing jagged little things. But we're going to relate these things because in a practical case, they are related. If the deformations are small enough, the slopes of points stay close to zero. Okay, so that's going to be the key thing. We're going to assume that the slope of our beam never deviates much from zero. It stays close to horizontal at every point. Okay, and so for the slope close to zero, let's re-investigate this function for curvature. The curvature can be approximated by something a lot better because you end up with that f prime in there that's squared and messes up the whole denominator. That ends up being zero. You just end up having a denominator that's basically 1 to the power of 3/2, which is 1 back again. And so the curvature just ends up being approximated by f double prime. And that's way, way better. Okay? The function f for us is the deflection of the beam and so like if this is your original beam and this is your deformed beam, so this is red is undeformed, black is deformed, then the deflection is this. And I'm going to call it V. If you have, if the deformed beam is above its original position, then V is positive. And if the deformed beam is below the original position, then V is negative. Okay, so let's look at these. So for the part from here to here, is the deflection of this beam positive or negative? Positive. From here to here, positive or negative? Negative, positive, negative. Okay, so that's what this deflection is going to mean. And with our simplification, we can rewrite that Euler-Bernoulli beams, elastic beams equation as So before we had that uh, m over ei was equal to this hideous expression for the curvature. Now we have a nice expression for the curvature, and we can write this as internal bending moment over e times I is equal to the second derivative of the deflection as a function of x. Okay, so that made our lives way, way better. And so now what we're going to do is once we come up with functions for the bending moment, we're just going to do the differential equations, integrate that equation in order to calculate the deflection. When you have an expression that you need to integrate, uh, what's the other step that you need besides just so you integrate that differential equation, and then there's something you have to do.
You need to have a setting condition.
That's right. So you need to use the boundary conditions in order to solve for your constants of integration.
I must run this movie that it was unbent at the time, so 0. Has that
Yeah. So there will be three types that we'll use, and I'll give you those in a second. So we'll solve this differential equation. And that means that we're going to need boundary conditions. And so our boundary conditions are the following. The first one is if the beam goes over a pin or a roller, or has a pin or a roller anywhere, then the deflection at that point is equal to 0. Let's say V is equal to 0 at the joint. So let me just sort of illustrate why this is. So if this is your undeformed beam, and you have, let's say that you have a pin here, and you have a roller here. Okay. And then you can apply any kind of crazy forces you want to this. This beam can do a lot of things, but one thing it can't do is change its height at the location of the roller or at the location of the pin. So this could do this, you know. But at the roller and the pin, V has to be equal to 0. The second type of boundary condition is, well, what about at fixed joints? Like a weld joint. So that would be a case like your beam connected to a wall over here. Okay. What restrictions does that put on the beam? Well, as long as the weld or the glue or whatever holds, this has to leave the wall at the angle that it starts with. Okay. And so that height can't change because of the weld, and the angle can't change either. And so our restriction in this case is that V is equal to 0 and V prime is equal to 0 at the joint. And then the last thing is, so remember that the internal bending moment is a piecewise function, right? And we'll have one function that represents it up to a point, and then another function that represents it after. That's why we do the cuts. Okay. So at the places, I'm going to call them seams, at the places where one cut ends and the next cut begins, there are restrictions on that because it has to be the same beam. And so at seams, and these are the points between cuts. I don't really have a way to draw a picture of this, but at the places where a left cut joins to a right cut, what we have is that the deflection of the left part has to match the deflection of the right function. And the slope using the left function has to match the slope using the right function at the seam. Okay, so we'll do some examples of that. The first example I'm going to do is a pretty simple one. And then we'll get into these boundary conditions later. Yeah, I guess we need these boundary conditions. Okay, so let's do an example. Where we have a cantilever beam. And let's say that the length is 3 meters. And the only thing that's making this deflect is its weight. So let's say that the mass of this beam is 50 kilograms. And we want to calculate the deflection as a function of x. Okay, so I'm going to start with a free body diagram. Of the whole thing. At the fixed joint, we have a reaction force and we have a reaction couple. We'll call that MR. And then at the midpoint, we have the weight of the beam, which is 50 times 9.81, so 490.5. Newton's second law says Rx, Ry plus 0, negative 490.5 is equal to zeros. And so R is equal to 0, positive 490.5. And then we'll use the moment equation. And we have, I'll do my moments about this point at the left. So we have positive MR, plus or minus a moment arm of 1.5 and a force of 490.5. And that's equal to 0. That is a clockwise rotation, so it's negative. So MR is equal to 735.75. But in order to use that deflection equation, what we need is the internal bending moment. So I have to do a cut. And this one cut will represent the whole thing. We have an upward force of 490.5, a couple of 735.75, and then we have a distributed load representing the weight. That is a total weight of 490.5 divided by 3. So 163.5 newtons per meter for that distributed load. And then we have our internal loads. There's our tension, shear force, bending moment. And to do calculations, we have to represent this distributed load as a point force. So the point force would be right at the middle of the rectangle. We have a width of x, a height of 163.5. And so now I can redraw this free body diagram. And we have a force at the middle. You know, the area of this is 163.5x. So we have a downward force of 163.5x, an upward force of 490.5, and internal loads. My about point is going to be at the left. And so I'll start with Newton's second law. We have 0, 490.5, plus 0, negative 163.5x, plus t negative v is equal to zeros. And so there's no internal tension. And the internal shear force is negative 163.5x plus 490.5. And now we can use the moment equation. The 490.5 doesn't produce a moment. The 163.5x is a negative moment with a moment arm of x over 2 and a force of 163.5x. And then we have our usual plus m minus vx is equal to 0. Yep, very good. We do, and I left it off. 735.75. And that would have messed up this calculation.
That won't produce a moment.
What?
The one isn't about the about point.
Well, couples, remember, don't change when the about point changes. So even though that is at the about point, that moment doesn't change. Okay, so we have so positive 735.75 minus x over 2 times 163.5x plus m minus vx is equal to 0. And so this says that m is equal to positive 81.75 x squared minus 735.75 minus 163.5x squared plus 490.5x. And then combine everything and you get that m is equal to negative 81.75x squared plus 490.5x minus 735.75. So that is our internal bending moment function. And that holds for the whole beam. Okay, so that was a lot, and I was going kind of fast, but you've seen all that stuff before. We're just calculating the bending moment. So now, why do we want the bending moment? Now we're going to go to the deflection equation. So the deflection equation says m over EI is equal to the second derivative of the deflection. And I'm going to write this as m is equal to E times I times the deflection. Am I going to do that? No, I'm not. I'm going to leave it the way it was. It was better before. And so now all we have to do is integrate this twice. So we have V double prime is equal to, I'll write it as 1 over EI times the quantity negative 81.75 x squared plus 490 x minus 735.75. And so V prime is equal to, I'm just going to integrate this thing. So we have
Is 1 over EI constant or the
1 over EI is constant. Yep, that's just the Young's modulus of the material and the area moment of inertia of the shape. And so integrate this first one. And you get negative 30.583 x cubed plus 245 x squared minus 735.75 x. But we've done an integration, so we need a constant of integration. Okay? And now we'll do it again. The deflection is a function of x is equal to 1 over EI times, integrate this thing. So we have negative 7.6458 x to the fourth plus 81.667 x cubed. Yes?
first term integrated the first time is supposed to be 7.25?
Which one?
The x squared term integrated the first time.
Oh.
30.58. I think it's.
Oh, you're right. I entered that in wrong. Thank you. 81.75 divided by 3 is 27.25. 27.25, and then that changes this one. 6.8125. Bless you. 8125. And then minus 367.88 x squared. Don't forget to integrate c, so this becomes c1x. And now we have a second constant of integration, c2. Okay, so all that's left is solving for those two constants of integration. C1 and C2 using the boundary conditions. And the boundary conditions are V, when x is equal to 0, is equal to 0. And V prime, when x is equal to 0, is equal to 0. Well, you really love it when your boundary conditions are at x equals 0 because it makes all this really easy to calculate. But what you would do is plug 0 in for all these x's and calculate these things. I don't have time to go through that carefully, but hopefully you can figure that out. I'll give you a couple of problems to try to work through. This says that C1 and C2 are both equal to 0. And so your final function for the deflection is equal to 1 over EI times the quantity, negative 6.8125 x to the fourth, plus 81.667 x cubed, minus 367.88 x squared. And that'll give you the height above the original for every x value in this beam due to that. So in this case, would you expect your v values to be positive or negative or mixed at different points? In this case, it's all going to be in one direction. All that's happening is the weight is pushing it down. And so all of those v values are going to be negative. Okay, and we expect them to be very small. This is, well, depending on the material, I didn't say what it was, but say you put steel in and you put, some reasonable cross section, you would get very small deflections that get bigger and bigger as you go towards the right end because the weight of the whole thing is tilting it down. Okay, that's all. Hi.